where we had wrapped up last time was dealing with cascoding our current mirror in order to, we were cascoding the current mirror in order to increase the output resistance of our current mirror such that it would behave more like an ideal current source. Now with this particular configuration, where we had transistors that were cascoded, what we found is that our VD4 voltage here was a little bit more than it needed to be, right? So we want transistor M4 to be in saturation, which means the lowest possible voltage that would keep it there would be 1 VD sat, and instead it is at a potential of VD sat plus VTH. So today we're going to talk about how we get rid of that extra VTH worth of biasing voltage there. And this is going to be accomplished by using what is called the wide swing. Next page, there we go. Here we have option number 4. The wide swing, also known as the high swing cascode current mirror. So we're going to start with a similar layout, okay? Here's our reference current, IREF. Actually, no, I'll leave it there. It'll be fine. Here we have transistor M1. Here is M3. Here is M2. Here is M4. And I'm going to tie our gates together for M1 and M2. And I'm going to tie the gates together for M1 and M3. Okay. So for our regular cascoded current mirror, don't draw this because you're going to have to erase it in a second anyway. We would tie the drain of transistor M1 to the gate of transistor M1 like so. And we would also tie the drain of transistor M3 to the gate of transistor M3. And this gave us problems, right? So we're going to break these connections and talk about what we need to have happen to make this thing operate at the minimum possible voltage. So here are our criteria. First, we need VG1. That's this voltage right here. To be biased low enough such that our voltage VD4, which occurs here, is equal to exactly 1 VD sat. So the minimum possible voltage that will keep transistor M4 in saturation. Secondly, we want transistor M2 to draw a current of Iref. So effectively, we want this to still behave as if it were a current mirror. And third, we want, that's not how you spell want, our voltage VD2 at this node right here to be as small as possible in order to maximize headroom. How we are going to accomplish this is we are going to alter our feedback connection and add an additional transistor, okay? So right now, M1 through M4 are identical. We are going to keep this portion, okay? Now, I'm going to, instead of making transistor M1 diode connected, I'm about to do a funky connection here. I'm going to tie the drain of M1 down to the gate of M3. I'm going to give myself a transistor over here on the left-hand side. This is going to be transistor M5. Like so. It's going to be diode connected. And connected to our reference current. Here's our voltage VDD like so. And the gate of M5 is going to be tied to the gate of M1. And then our aspect ratio of WL over 5, or of transistor M5, is effectively what we are going to figure out what it needs to be in order to force all of our voltages and currents to behave the way that we want them to. Okay. So I'm going to call this voltage here VG3. I'm going to call this voltage here VD3. And I think that's all the voltages that I need to identify because the source of M1 is at VD3, the source of M2 is at VD4. So I think we've got everything kind of taken care of here. Okay. So if we look at this connection, we can see that our voltage VG3 is equal to VGS3, right? Since the source of transistor M3 is at ground, and therefore this voltage VG3 is equal to VTH plus 1 VDSAT. In order for us to make VD4 equal to 1 VDSAT, we will need VG1 to equal VGS2, excuse me, plus VD sat. So let's think about what I'm saying here, just to be clear. All right. So for VD4 to be equal to VD sat, VG1 needs to be VGS2, which is this voltage right here, plus 1 VD sat. Okay, so that checks out to me. If we did Kirchhoff's voltage law, VG1 should be equal to VG2 plus VD4. And if we want VD4 to be equal to exactly VD sat, then this is the constraint that we have on VG1. Okay, so to make this happen, we have to size M5 such that VG1 is equal VTH plus 2 VD sat. Right. So just making sure that my peon brain here makes sense of all of this kind of stuff, because I wrote these notes over a year ago. So if VG1 is equal to VTH plus 2 VD sat, then that would mean VTH plus 2 VD sat is equal to VGS2 plus 1 VD sat, where VGS2 is just VTH plus VD sat. So that all seems to check out up here. Okay. So we need VGS5 to be equal to, or sorry, VGS5 will be equal to VTH plus the square root of twice I reference divided by mu n C ox times the aspect ratio of transistor M5. And we need VG1 to equal VTH plus twice VD sat, which would be VTH plus twice the square root of twice I ref over mu n C ox W over L 1 through 4. Are we okay with this thus far? Stephen, how are you feeling?
No, part of what was throwing me off was the way it was written, the 2I/1-4. I'm beginning to see it a little bit now. You're saying the aspect ratio MOSFETs 1 through 4.
Right. So effectively, in order to make this thing work, the aspect ratio of 5 is going to be different from the aspect ratio of 1 through 4, which are all the same thing, right?
Right.
All of them are carrying the same current IREF. all of them have the same values for mun and Cox because that's common to the technology node. They'll all have the same threshold voltage. The only thing that we have control over is the aspect ratio. And we're trying to figure out what aspect ratio will force this thing to behave such that transistor M2 is properly mirroring the current while VD4 is as small as it can possibly be while keeping M4 in saturation. This is achieved by sizing transistor M5 to a, I don't want to say specific value, like we are going to get a number, but that number is really the minimum size for this thing. We can make it larger than that and it'll still work out correctly. So these are our constraints in order to make VD4 equal to VSAT. Okay. So if we look at our diagram here, VGS5 is the difference in potential between the gate of node 5 and ground. And since the gate of transistor M5 and the gate of transistor M1 are tied together, VGS5 and VG1 actually represent the same voltage, okay? So if we equate these two things, since VG1 must be exactly equal to VGS5, that means that VTH plus twice the square root of twice IREF over mu n Cox W over L 1 through 4 has to be equal to VTH plus the square root of twice IREF over mu n Cox W over L for transistor M5. So hopefully we can see that we can subtract a VTH from both sides, eliminating that part. And what I'm going to do now is I'm going to move that 2 inside that square root sign, right? So if I move 2 inside, I'm going to have the square root of twice IREF times a factor of 4 over mu n Cox W over L through 4 needs to be equal to the square root of twice IREF over mu n Cox W over L of transistor M5. So what does this tell us? Well, effectively, what's going on here? 2 is a constant, IREF is a constant, mu n times Cox is also a constant. The only things that have any variance here are our aspect ratios, right? So if we have a specific aspect ratio for transistors 1 through 4, then transistor 5's aspect ratio turns out it has to be at least 4 times as large, this number right here, in order to force these voltages to be equal, right? From this, we can see that W over L of M5. Sorry, got this backwards, 1/4 W over L of 1 through 4. So we make it 4 times as long in order to accommodate this, right? So effectively, if we did some math here, if we pull our L's out from here and put it up here, these things will be equal if W over L of 1 through 4 times 1/4 is equal to W over L of 5. Yeah, sorry, got my algebra in my head. Messed up a little bit. So under this constraint, sorry, W over L5 is equal to 1/4 W over L of 1 through 4. Then VD4 will be exactly 1 VD sat. That's the purpose of all of this. This in turn sets VG1 to be exactly VTH plus 2 VD sat. Let's look up here real quick. So what we're going to figure out effectively is where VD2 is going to be in this thing now under this constraint to see what our headroom looks like, okay? So we need VDS2 to be greater than or equal to VGS2 minus VTH in order for transistor M2 to be in saturation, right? So VDS needs to be greater than VGS minus VTH for saturation to occur. Since we're looking at transistor M2, then VDS2 equals VGS2 minus VTH is our minimum requirement for saturation. So VDS2 needs to be at a minimum equal to VGS2 minus VTH. This keeps M2 in the saturation, okay? Well, VDS2, let's scroll up here, is simply equal to VD2 minus VD4 because the source of transistor M2 is connected to the drain of transistor M4, right? So we will have VD2 minus VD4 is equal to VGS2 minus VTH. Well, let's look at VGS2. So VGS2 is VG1 minus VD4. Minus VTH. From this, we can simply add a VD4 to both sides. So this is going to look like a VG1 minus VTH Well, VG1 is VTH plus 2 VD sat minus VTH comes out to be just twice VD sat. So this is our minimum value for VD2. So we actually have the most amount of headroom we could possibly have by using this configuration, because both transistors M2 and M4 are carrying our reference current, but are biased on the absolute edge of saturation. So we have a wide swing current mirror because we have the maximum possible amount of headroom up to our biasing voltage VDD to utilize for our connections. So this is the benchmark effectively for current mirrors in high performance integrated circuits. All right. So what we're going to talk about now is, we scroll back through here. This particular circuit uses ideal current sources. This one also used an ideal current source, and so forth and so forth. We can't actually bias these things. Let me open up a new instance of this. Engineering paper 12 sheets. Remove this. So we are about to talk about biasing current mirrors. And what we are talking about specifically is, what do we replace our ideal current source with? Okay. So we have multiple options, as we always do, and we will go through them in order of most impractical to most practical. And they obviously get harder to understand as we go through. So our most impractical option is simple resistive biasing. So I could replace my reference current with some resistor R bias, like so. And down here is my current mirror. Here's M1, here's M2. So in this case, the current that's flowing through our bias resistor is our reference current. So whatever current that is winds up flowing into the drain of M1 and then gets copied over here in transistor M2. Okay. So we can figure out what this reference current is going to be in terms of our bias resistor simply by using Ohm's law. Okay. So using Ohm's law, our reference current, IREF, is going to be nothing more than VDD minus VGS1 over our bias. And just to be clear that everybody's on the same page, this is our voltage, VGS1. Okay. Because M1 has to be in saturation because it's a diode connected device, we know that VGS1 will be equal to VTH plus the square root of twice I ref over UN C ox times the aspect ratio of transistor M1. We're going to use this in a minute, actually several minutes, but for simplicity's sake, we are going to call this quantity beta 1. So I am using it for simplicity's sake. Better engineers than I use it because it's effectively a representation of, it's a holdover from doing this with BJTs, effectively, where they have certain scaling, or what is it? It's the common emitter current gain, which for us would be a common source current gain. And we have a common source here because our source is tied directly to ground. Okay. So this is the MOSFET equivalent of the BJT beta effectively, and conveniently enough, it allows us to not have to write that whole thing down over and over and over again. Okay. So from this representation, we find that our reference current IREF is equal to VDD minus VTH minus the square root of twice IREF over beta 1. And all of this is divided by R bias. Okay. I did throw this into my MathCAD to do a symbolic solve and see if there was a way that I could express this in a little less of a pain in the ass form. And the short answer is very much no, unfortunately. So this is definitely a throw this into your system solver for a specific reference current to solve for the resistor value, or if you put the resistor value in, you could iteratively solve for your reference current. Okay. So there are a couple of problems with this scheme of establishing a reference current. The first of which is that we can see that our reference current is linearly proportional to our power supply voltage, which means if our power supply voltage changes, our reference current changes by the same amount, and that is problematic. Okay. Additionally, our reference current utilizes a specific resistor value to achieve that reference current, which means if there are process variations or temperature variations, we now have an incorrect reference current as well. Okay, so this works, it just works incredibly poorly. What I want us to do here, just really quickly, is to do some math to also come up with another problem of this biasing scheme. Okay, so let's say that we have a process technology node. Example. So this is a VDD is equal to 5 volts technology node. These aren't the exact values for C5 process, but they're pretty close. Okay. So for NMOS transistors, we have a minimum aspect ratio that is 10 to 2. same exact value for PMOS. We have a threshold voltage VTHN that is 0.7 volts, and threshold voltage for our PMOS transistors is negative 0.8 volts. UNCOX is 400 microamps per volt squared. PCOX, because of the lesser hole mobility, is about 115 microamps per volt squared. So if we want to establish a 25 microamp reference current, how large will our resistor be? Simple question. We are going to assume that we are going to use the minimum possible transistor size to accomplish this. Okay. So if we use the equation that we developed, we would have 25 microamps is equal to 5 volts minus 0.7 volts minus the square root of 2 times 25 microamps divided by 100 microamps per volt squared times 10 over 2. This whole thing divided by R bias. And what we would find is that our bias resistor would come out to be 165.675 kilohms. So why is that potentially problematic?
We have to round it to get to a whole value if you're doing a C5 process. Not so much an issue.
It's not the fact that it's not a nice, neat value. It's the fact that it's friggin' huge, right? So if we are dealing with a process in which our largest resistor only has a resistance of about 1 kilo ohm per square, then we need to make a resistor that is about 166 squares long or whatever, right? That's a beefy resistor. Even if we utilize a serpentine resistor pattern, this is going to take up physically a large amount of area. We are also going to see, because it's such a large resistor value, and because to achieve this particular reference current, we need exactly this, that as temperature fluctuations occur or any misalignments occur, we are going to see wild swings in what the actual reference current we get out of this thing are, okay? So it can be done using a resistor. Don't do it if you want any level of precision in your reference current. Okay, bad idea.
Although it was making transistors.
Exactly right. Yeah, if you're slapping together something easy peasy or whatever, this is fine. If you want to use this for cell phones or anything like that, hottest of garbage. Can't be done. Right? Think about you using a cell phone, right? You have a system in which your supply voltage constantly decreases as you utilize the device, which means you're constantly changing your reference current, which means all of your transistors behave more and more shittily as your phone call goes on, or as you Google more stuff, or text people, or whatever it is. Look up cat videos on the internet, etc. Right? Resistive biasing is garbage for performance ICs. Works great for discrete level things, not really great, but it's the thing that makes the most amount of sense because you cannot guarantee transistor matching or anything like that. So making a discrete component, amplifier, et cetera, using resistors makes sense. You have a lot of control over what the values are. In an integrated circuit standpoint, you don't have nearly enough control to make sure that this particular resistor value stays this resistor value under all of the different operating conditions that you might be in. So problematic at best.
So I was wondering about that because as an example of cell phones, there have been analog cell phones, very big devices,
Yes.
very few integrated parts.
Right.
And a lot of those, I've actually seen one open up, lots of resistors in places used exactly for resistive bias.
Right.
So, and you could get away with that because very few integrated parts. You have like maybe one or two integrated chips.
And
Yeah.
accuracy didn't matter at the time.
No,
There were
no.
like 12 people in a city on a cell phone.
Right. So that's another very, very important thing. The channel selectivity did not have to be nearly as precise. So your filters and all that kind of stuff didn't have to have nearly as high Q values because you're not having tens of thousands of users actually operating on the same extraordinarily narrow frequency band.
Probably
So
also a lot more noisy and they're probably transmitting with a whole lot more power.
yeah, yeah, the batteries and all that kind of stuff were definitely a lot beefier.
There are videos out there on how all that works. It's intense.
Well, I mean, it's basically a handheld radio transmitter.
That is exactly what it is. Yeah.
That's what it is.
But yeah.
Analog to digital.
All right. So this is one scheme for doing it. Isn't the best. Okay. So now let's look at using a MOSFET. So effectively in this next scheme, we are replacing this bias resistor with a transistor, but we are going to do so under the constraint that we need to force the transistor that we're adding to also be in saturation so that we have stability. That will, to some extent, largely eliminate the temperature dependence because the transistor is going to behave like a transistor. Like we're going to have some mobility related effects, but that's all happening underneath the square root sign. So it's not a linear relationship. So it's a little bit better. Okay. So option number 2. Is diode connected MOSFET biasing. This is an interesting scheme, and I'll explain what I mean by that momentarily. But effectively, what it looks like is this. We have our supply voltage, and then I'm going to put a PMOS transistor up here. An NMOS transistor down here. And I am going to make both these transistors. So this is M1 and this is M3. Both of these guys are going to be diode connected. So that means the gate of M3 is actually tied to the gate of M1 as well, since our diode connection means that we need our drains and our gates tied together. Okay, so this is intuitively interesting, I think. And then there's another interesting aspect of it. So this scheme can be used to mirror currents in an NMOS current mirror, but also in a PMOS current mirror, excuse me. But not both simultaneously. It's either or. Okay. And we'll explain why it's either or in just a moment. So effectively, M3 is going to be carrying some current IREF. It could be supplying it, or it could be the current mirror part. M1 will be carrying a current IREF. It could be supplying it, or it could be taking it in as the current mirror part. And then depending on which part is acting as the resistor and which part is acting as part of the current mirror tells us what's going on out here. So if M1 is part of the current mirror, M2 will carry IREF. If M3 is part of the current mirror, M4 will carry IREF. So it's a very interesting connection because of its versatility, in my opinion. But it's a little less obvious to understand. So effectively, what's going on here is, let's say that transistor M3 is replacing our resistor from our previous example, so that our current mirror is established by M1 and M2, okay? That means that we would have some voltage here, VGS1, and we have some voltage here, VGS2. And if we want M1 and M2 to be as small as possible, that means that the SG3 needs to be very large because it has to take up all of the additional voltage difference between VGS1 and VDD, okay? So effectively, if M1 is normal sized, M3 has to be very large to accommodate that large voltage drop over it while maintaining that same reference current flowing through it. And vice versa. If M3 and M4 are small, then M1 has to be physically larger in order to accommodate that larger voltage drop while maintaining that exact same current flowing through it, okay? So we can describe this mathematically simply by using Kirchhoff's voltage law. VDD, our supply voltage, will literally just be VSG3 plus VGS1. Since both of these transistors are being forced to operate in the saturation region, that means that VSG3 will be the absolute value of our P-type threshold voltage. I'm using the absolute value signs because I expressed our P-type voltage as a negative quantity earlier, plus the square root of twice I reference over mu P Cox W over L3 plus VTHN plus the square root of twice I reference over mu N Cox W over L1. So this is our governing equation of how this thing works, okay? So let's look at how large physically our transistors will wind up being if we employ this scheme, okay? So we're going to be utilizing the same technology node that we did before. So let's look at case one. PMOS biasing. And so by that, I mean our PMOS device is taking the place of the resistor. So we would have 5 volts is equal to 0.8 volts plus the square root of 2 times 25 microamps over 115 microamps per volt squared times the aspect ratio of WL over 3, which is what we're solving for, plus 0.7 volts plus the square root of 2 times 25 microamps divided by 400 microamps per volt squared times 10 over 2, where I'm assuming here that we're making our current mirror as small as physically possible. If we solve this guy for W over L 3, what we find is that the aspect ratio of transistor 3, M3, has to be 0.039. Since this is less than 1, that means the length needs to be larger than the width. So if we keep the width at its minimum possible value of 10, we would find that W over L3 would be a 10 over 255 transistor. Large, but actually not as large as the resistor would be in and of itself. Okay. If we look at our second case, sorry, this should be NMOS biasing, excuse me. We'll have practically the same equation, but now the aspect ratio of our PMOS transistor is the known quantity, and the aspect ratio of our NMOS transistor is what we're trying to solve for. Solving this guy for the aspect ratio of transistor M1. We would find that this would be 0.012. So an even smaller aspect ratio, which means the length will be even longer. Assuming that our width is at the absolute minimum that we can have, which is 10, this is going to wind up being a 10 over 830 sized transistor. Okay. All right, so this particular configuration eliminates or mitigates, I guess would be a better term, since mobility is definitely temperature dependent. Mitigates the temperature dependence issues that using an actual resistor contributes. But there is still dependence on the power supply voltage, right? Because this equation is literally VDD is equal to this other stuff. The textbook has a mathematical derivation of stuff. Effectively, what it boils down to is you get about on the order of 10 microamps of change in reference current for about every 1 volt in power supply variation. So if you're trying to establish a 25 microamp current and your power supply fluctuates by as much as half a volt, you're losing or you're getting plus or minus 5 microamps of current added on to your reference, which
It's a
is,
large percentage.
yes, exactly right. It is still quite significant, okay? So let's stop here. We are going to deal with our third option, the beta multiplier reference circuit, next class. The beta multiplier reference circuit is a integrated circuit spin on the Widlar current source that we talked about in 336, where the Widlar current source is what is used in op amps to transform your voltage, or excuse me, transform the currents leaving your power supply, your external power supply, into these small bias currents for the internal circuitry of the op amp itself. Okay, so we're talking about a circuit for its original intention converts amps worth of current into milliamps or smaller worth of current. So that's what its original purpose was. Yeah, so we'll kick that off on Monday, and then I have a decision to make. So after we talk about the beta multiplier reference circuit, and you realize how freaking awesome it is at doing its job of providing extremely stable reference currents with very little, so no supply dependence whatsoever and very small temperature dependence due to its using a resistor, then the most obvious thing to me to do would be for us to start talking about the differential stage of the op amp, okay? Which would be a review of differential amplifiers. Then we'll talk about, I think in 336, we didn't really cascode things or anything like that with differential amplifiers. We just left it as single transistor devices and all that kind of stuff. So we'll talk about cascodes. The reason why I say I'm slightly confused here is because the textbook, trying to actually kind of follow along things now that we're getting into the meat and potatoes of design, and that's what the textbook is all about, is designing these damn things, or at least chapters 20 through 24 is that the next chapter of the textbook talks about amplifiers, single stage amplifiers. Now, we've already talked about common source, common drain, and common gate and all that kind of stuff. So I don't want to redo those again because that's boring. At the end of this, of that particular chapter though, it talks about output stages, which is something that we absolutely need to do. But to me, it doesn't make any damn sense to talk about output stages before we're at that point in our design. So I think I'm going to skip chapter 21 and we'll circle back around to what's needed once we get to that. Does that seem like a reasonable thing? So we've been skipping all over the damn textbook all over the place. Anyway, we are going to keep it up. All right.
Well, the Moses schools do it, so why not us?
Yeah, fair enough. That's a very, very good observation. All right. So that's enough ranting out of me for today. I'm going to go grab a sandwich.